All right, so we've got Rolle's theorem and mean value theorem. Rolle's theorem says if a function f is continuous, meaning you don't pick up your pencil basically to draw it, on the closed interval from a to b, and it's differentiable on that open interval, if f at a equals f at b. Here's what that's saying. Here's the function right here. This is f of x. If you take a value a, I'm going to call it 1. Why not? If I take a and I 1 and I plug it into that function, let's pretend I get the number, I don't know, 4. And then let's say I take b, I'm going to call that, I don't know, 8. I'm making this up. And I plug 8 into that same function and I also get 4. If these two are the same number, here's what Rolle's theorem says. Then there's at least one number, we'll call it c for now, we don't know which one it is. There's a number where the derivative of the function is 0. In other words, where there's a tangent line that has a slope of 0. Because you had to go up or down to get back to that point. You know what I'm saying? Does that make sense? Now, some of you guys are already kind of ahead of me going, well, what if it was just a straight line? Well, if it was a straight line going straight across, isn't that tangent slope always 0? So it's already 0. So that's kind of where we are with Rolle's theorem. Mean value theorem is very similar, but the slope isn't necessarily going to be 0. It could be anything else. The mean value theorem says that if f is continuous on a closed interval and differentiable on the open interval, so same kind of rules, then there exists some number c in between the interval so that the derivative at that point equals the average slope. So they're saying that at some point on the interval, the instantaneous rate of change is going to be equivalent to the average rate of change. In real people language, here's what this means. If I drive an average of 75 miles an hour to get from here in Tulsa to my in-laws in Oklahoma City, I might drive 80 for part of that drive and 40 on the city streets. I had to have driven exactly 75 miles per hour at some point on that trip. Does that make sense? Because I'd have to cross through 75 before I hit 80. Does that make sense to everybody? So at some point on that trip, I had to have hit 75 miles per hour because that was my average. So you can kind of see this little funny joke I found on Pinterest. That's a mean value theorem. It's being very mean. Your mother was a hamster and your father smelled of elderberries. That's from Monty Python and Search for the Holy Grail. If you haven't seen it, it's a very funny movie, especially if you watch it twice. It's not as funny the first time. And then here's a picture of the actual mean value theorem. We've got this point on the function. We have this point on the function. This is, I don't know how fast I'm driving maybe. So I slow down and I speed up. This is the average speed right here. If you'll notice, right here at C, this point has the same tangent slope. And actually, that same tangent slope is right there. It's in two places on this one. So the mean value theorem said that there's at least one point where you're going to hit that slope, that average slope. And then my little note down there that Rolle's is a specialized version of mean value theorem, but the rate of change is 0. It could be anything on this guy. It could be -2, it could be 100. Here's our examples of what your book is going to look like today. Or not your book, but your assignment. It says determine whether Rolle's theorem can be applied to f on the closed interval AB. Let's stop there. In order for it to be able to be applied, what rules have to be followed? Has to be continuous, and what else? Differentiable. So let's look at example 1. Is that a continuous graph? Yeah, it's continuous. Is it differentiable everywhere? Yes. So it follows both of those rules. And because this is my notes, I'm going to make little notes here so that I know when I get home tonight that I'd actually check, is it continuous and is it differentiable? So far, Rolle's theorem will apply. The other thing that happens is that f at A has to equal f at B. This is A, this is B. So let's try it here. F at, whoops, don't put A, sorry, 0, my bad. And f at 3. We have to find f at 0 and f at 3. Well, if I plug in a 0, what do I get? 0. What happens if I plug in a 3? 0. So f at 0 equals f at 3. Check. So Rolle's theorem will apply because all three things are true. Then it says, if Rolle's theorem can be applied, find the values of c where the derivative equals 0. So I need to find the derivative. And they want that derivative to be 0. So let's set it equal to 0. Should get 3 halves. So x, or c, they want it to be called c, is 3 halves. And that's all you have to do. They're saying that at this point, when x is 3 halves, that's when the slope is 0. Questions? Let's look at the next one. Is this a continuous function? Probably. Is it differentiable everywhere?
Yeah.
What do you do if you're not sure? Can't you take the derivative and find out? Let's take the derivative. Let's just check and see. So we think it's continuous. We're checking for differentiability. We take the 2/3, throw it to the front. So I have 2/3 x to the negative 1/3. That's the derivative. If I rewrite that in a way that makes more sense to me, I've got 2 over 3 times the cube root of x. Right? Okay, is there anything x can't be? Can't be exactly 0. Could be anything else, but it can't be exactly 0. So if x can't be 0, is 0 on the interval they gave us? Yep. So Rolle's theorem does not apply. So it says if Rolle's theorem cannot be applied, to explain why not. So we would say something like, because f of x is not differentiable at x equals 0, Rolle's theorem does not apply. That's really messy handwriting, but you get the idea. Any questions for what I did and why I did it? Everybody okay? And that bell is about to ring for lunch, so we'll stop here for now, okay? All right, so the third example, remember we're talking about Rolle's theorem, and you guys just go back from lunch, so you kind of turn your brain off for a little bit. We've got to check first to see if it's continuous and differentiable on the interval. So it's an absolute value one, so we know it's continuous. The differentiable part is a little tricky. Absolute value, you know what that looks like. What does that look like? It's a v, and we do have this little -1. What did that -1 do to it? Just shifted it down 1. So we know it's not differentiable at what? At x equals 0. Because, here's our graph. Here's our new graph. There we go. It got shifted down 1. That's a sharp corner, right? So when x is 0, it's not differentiable. So Rolle's theorem does not apply. So we just say Rolle's doesn't apply because f of x isn't differentiable at x equals 0. And that would be fine. So there's Rolle's. The mean value theorem. So to determine whether the mean value theorem can be applied to f on the closed interval. So first, it's the same kind of deal. We have to decide, can we even use it? It needs to be continuous and it needs to be differentiable. So when we look at number 1, is sine of x continuous? Yeah, it looks like this, right? Is it not differentiable anywhere? No, it's fine. So we can apply it. So let's do that. It says that if it can be applied, find all the values of C in the interval such that, use this equation, the instantaneous rate of change equals the average rate of change. So because this is my notes, I'm going to say, yes, I checked that it was continuous. Yes, I checked that it was differentiable, just so that when I get home tonight, I can remember what we talked about. All right, so we go ahead and we use this equation right here. We say the derivative at C equals f at b, this is a, this is b, so f at pi minus f at a, so f at 0, over b minus a, so pi minus 0. Everybody see where I got all that? I just plugged in pi everywhere I saw b, 0 everywhere I saw an a. So the function at pi, if I put a pi in there, what is sine of pi? 0, I heard it. Minus, put in 0 into the function. What's sine of 0? 0. And pi minus 0 is pi. So they want us to see, or they want us to find the place where the slope is 0. It won't always be 0. It just happens to be 0 this time. So the average rate of change was 0. So we say 0 equals the derivative. What's the derivative of sine? Cosine. And where is cosine 0? Pi over 2 and 3 pi over 2, but here's our interval, so we only need pi over 2. Ta-da, done. Questions? Sure. So sine of x was continuous and it's differentiable, so mean value theorem will apply. We are trying to show that the instantaneous rate of change, in other words, the derivative at some point, equals the average rate of change between 0 and pi on the graph. So we use the little equation, f at b minus f of a over b minus a, where a is 0 and b is pi. So the function at pi was 0. The function at 0, when I plugged it in, was 0 over b minus a. So pi minus 0 was pi. So that was 0. This is the average rate of change. And maybe it would be good to write that down in your notes so you know what you're actually looking for. Average rate of change, average slope. Yes. So then the derivative at c is supposed to equal that, so we can solve for c. So I put this 0 here, and the derivative of sine of x here. So I solved and found out that pi over 2 is where that slope occurs. Tiffany, does that make sense?
Yes. How come it has like that same equation on the front and
Because this was, because that's the mean value theorem, and this question was all about Rolle's theorem. Rolle's theorem is just this piece right here, that if f at a equals f at b, then at some point it had to have a slope of 0.
So the back is just restated.
The back is only mean value theorem. Yep, no problem. Next little guy. Is this graph continuous on this interval? No. What can x not be? 1. There's an asymptote at 1. So we just say mean value theorem does not apply because f of x is, don't ever say it, is not continuous. Whoops, sorry, I misspelled it. At x equals 1. And that would be fine. It's a decent answer. Mean value theorem does not apply because f of x is not continuous at x equals 1. Last one. Is that equation continuous? We think so. Is it differentiable? We think so, yeah. Polynomials typically are. Just regular straight polynomials. So we think that's probably differentiable. So now we just need to use our equation. We know that the derivative at c is supposed to equal the average rate of change. To find average, we take the function at b minus the function at a, and then we take b minus a, where a is -1 and b is 1. So then we plug them in and we see if it works. The function at 1 would be 1 times 1 times 1 plus 2 times 1, so we get 3, minus the function at -1 is going to be -1 minus 2, so that's going to be a -3, over the 1 plus 1 is a 2. So we really have 6 over 2, which is 3. This time the average slope, the average rate of change is 3. So we need to find at what point is that tangent line 3. So we're going to take 3 and set it equal to the derivative. Derivative is 3x squared plus 2. Solve for x. So at 2 places, that says radical 3 over 3. Sorry, it's really messy. So at 2 places, we find out the slope is 3, where x is positive radical 3 over 3 and negative radical 3 over 3. Anybody have any questions? Okie dokie. That's pretty much it. Let me stop this and get you your work